This is a in case we don't have time in the class. Uh, this is a full pipeline for creating a data set, formatting your data set, and at the same time training using a pre-trained model and pre-trained weight. So I will guide you through like the full pipeline in this collab. The first thing that you need to do with the URL that we're providing in the presentation, in the deck, you want to go to the link, save a copy in your own drive. Don't run this because you will get like some errors. And once you copy it, you can connect to a runtime, your Colab. Always remember, so it runs faster, set the GPU, high RAM. If you don't have a Colab Pro, it doesn't matter. I'm not going to use it for now, but always remember to save to use the GPU. So in this case, I'm just going to add one thing. The first cell shows you, for example, that we are actually running on a GPU. In my case, we're running a Tesla P100 with 16 gigs of memory. So actually that is pretty good. So the first thing that we're going to do, and here you see a lot of things. This is, for example, the cell to create the folders for the data that we have. So if I update this, let me make this a little bit bigger so you can see. If I update the folder, we have a folder now that is for forks, knives, and spoons. So this specific collab basically is about the creation of a data set to classify items, for example, in your kitchen, right? I'm giving you the zip files containing knives, forks, and spoons, but if you want to create your own data set, you need to gather images from the items that you want to detect. It could be whatever you want. So in this case, for example, if you want to detect, I don't know, like cars, for example, like Tesla cars, you can go to Google and gather your own images. And in relation to this, if you go, for example, to Google, right, and if you look for puppies, for example, right, you can see like a lot of images like cute puppies, for example, or cats, or whatever you want, or whatever you want to classify. There is one extension that I recommend that you use. So if you go to Chrome, more tools, extensions, there is one that is called to download all images. This is a very nice extension that basically allows you to download all the images that you see in your file. So it's actually super cool. So for example, here, if you install the application and then, sorry, the extension, and I have it here, and if I say, for example, like download all the images of puppies, you just click here and it will download like whatever images that you have here. It's taking a little bit of time, but in the end, it will just create a zip file with all the images that you want to download in this case, right? So then it would ask you to download, like to just like where do you want to save your zip file, and you're ready to go. So you see here it's saying like what do you want to do. So here, puppies, I'm going to save it in my desktop, and if I go to my desktop, I see that I have something that is called puppies, and I have all the images, including, I don't know why there is a picture of me, but that's fine, because probably it was from my profile. So one thing that I recommend is that after you download the images, you also like clean a little bit. So there might be things that are not necessarily like puppies or things like that. You just do a quick check and you're good to go. So in this case, so for example, it downloaded also like vector images. We don't want that. So we can get rid of that. But we have like images of cute dogs, for example, here. We're not going to use this, but I'm just showing you the process of creating your own dataset. You can also take pictures in the street and just create a zip file with your images, right? So it doesn't matter. It doesn't matter for this purpose. Just like I'm just giving you an alternative to do this. So once you have that, in this case, you can basically, after you create the folders, you can automatically just, for example, let's see, I have a new, let me just create a new folder, puppies. And in this case, I want to just like drag the zip file to this folder. And of course, Colab is giving me the warning that if I upload whatever I upload, once I close the session, or if my computer crashes or the session crashes, you will lose all the data. So that is fine. We don't care about that. In this case, I am giving you, for this example, a pre-compile, let's say, like a set of images of knives, forks, and spoons. So the commands here, basically, after I create the commands, these are all terminal commands. This is why we have the exclamation mark at the beginning, so it can run with Colab. You can run these commands here. I'm accessing the directory. I am getting with this command the zip file that is hosted in my Dropbox account. I am unzipping the folders, and then I am just returning to the parent folder and doing the same thing for knives and forks and spoons. So, for example, here, I'm just going to erase this because we don't need it. Basically, this is where automating the process that I just did with the puppet, just automating the creation of the folders. And also, in this case, for you, I'm just automating the process of just uploading a zip file. So I'm just going to delete this because we don't need it, of course. And now I will delete the folder and we're good to go. So in this case, I am to execute this cell. So you see that this is downloading and it's inflating all the files for spoons and forks. So now if I update the files, if I see the fork folder, and there is a slight error here. So knives, forks, and spoons, for some reason. This is not correct. Let me just do a quick check. Okay, so after you run this, of course, there was just like a typo in one of the URLs. So now, after you automate this process, you will see that it just unzipped all the images of forks, knives, and spoons. So you can do basically the same thing with your own data. Then we want to delete the zip files because we don't need them anymore. If you want to keep them, that's fine. We want to also show how many images, for example, we have here. So we have this amount, like 287, 207, and 186. And this is very important because we want to have the same amount of images for all the folders, right? So in this case, we're gonna just check, like this is some sanity check. We're gonna use pyplot, and basically we're just like reading from the folder knives. We're just getting with this list directory, getting all the names in our folder, and we are just plotting, in this case, like 25 examples, right, of images of knives. So this looks pretty good. Now, what we want to do, we want to create our dataset, and we will do it by automating the process again. We will create a folder that is called dataset. So if I update this dataset, we have forks, knives, and spoons. And what we want to do is copy the images from each folder to the dataset folder. So basically, we're getting the information from the forks, from the knives, and from the spoons. And we're going to basically copy all the information here to format it in a nice way. So this is why we do some import like shutil and os and fnmatch, because we are going to, in this case, we created a function that is copy the images, where you basically specify the number of images to copy and the name of the folder. So here we have the source folder. We don't need this actually, so I can comment this, and I can also get rid of this. So for example, here what we're doing, we're just specifying the extensions that we want to filter, because sometimes you can get images as JPEGs or JPEG, right? So we want both basically, because are the same file type, but with different extension. So this is why using list comprehensions in Python, basically we're in one just line of text, we're just automating the process of filtering and getting those files. In this case, why is that important? Because I don't know why, when every time I compress something, for example, in macOS, and sometimes in Linux happens the same thing, we get a folder. And if we don't run this, if we don't make like a check of this thing, we will get an error. So it's good to have this type of things. It's always good because this happens a lot when we're dealing with a lot of data, right? So this is copy everything in the destination folder. If I execute this, this is basically, when I execute this, I execute the code of the function. If you do something wrong, you have the option also here to delete all the files in the folders. I don't think that will be the case. This is pretty much like optional. But here, for example, we want to specify the images to each folder. In this case, if we go back, we see that we want to use this number, the lower number, right? So we are going to use that number here. You're going to say the number of images is 187. Let's just do like 185. It doesn't matter. This is a low amount of images, by the way. You might want to put more, but that's fine. So here, basically, we're using the function copy images with the number of images that we want, and also with the name referring to each folder. So we do this, and now if we go to the forks folder or the knives, for example, we see that we have all the images. So that is pretty good. And now we can also check how many images we have, and for some reason we have less images in one. So let me check that. What is that all about? Yeah, for some reason, I don't know why, it gave me the wrong number. We're using 179 images. It's fine. So in this case, for example, what I did, because I had a mistake, I just ran this cell, then I just deleted the dataset folder, I created the folder again, and everything was fine. And then I just rerun this two cells, and everything is fine. So after you do that, this is very important because we have only n amount of images. We can do some data augmentation to have more data, and that is amazing. So for that, we're just importing some TensorFlow Keras functionality. So one is called the image data generator. And what do we mean with data augmentation? So for example, here, data augmentation. Data augmentation basically is a technique that, especially when we're dealing with images, if we don't have enough data, we can enlarge our data set performing this type of operation. So we have the original image and we apply some mirroring, some rotation, some scaling to create more images from what we have. So you can find like a lot of references about this. So for example, here, this is a very nice diagram of what we're doing here. So for example, here you have a handwritten digit of number 6, but if you apply all of these operations like mirroring, rotating, scaling, or just like shifting the position of the image, you're fooling your neural network, making it believe that you have more data, and that is actually pretty effective. So this is why we create a data generator. So basically, we're normalizing the data. Again, we explained this on the slides. You might want to express your data as normalized. Neural networks like that to express your values between 0 and 1. You can apply, for example, like a rotation range, also like the shift in the width and the height, also a shear, for example, to deform a little bit the image, to have like a zoom, basically like zoom out and zoom in between like 0.5 and 1.5. And also this is very important because with the data generator, you are setting the split for testing later, right? So in this case, we're just like reserving 20% of our images when we want to validate. So also here for the generators, we're actually creating the training data set, right? And also here we are creating with this the testing data set. And basically here we're just specifying the folder where we're getting our images, what is the target size. And this is very important because we don't care at the beginning the size of the images. But in this case, the network that we're going to use uses 224 by 224 images. We are creating something that is called a batch size. So that means like we're going to create like batches of only 32 images for like hardware or like speed purposes. And then just for a sanity check, we're going to print 10 images to see what happens. So if we actually execute this, it will think a little bit. It says that it found 432 images belonging to 3 classes, and also like 105 images belonging to other 3 classes. So you see here our images were like scaled and properly like, I don't know, like modified to have more data. And now this is very important because this is a part that we talked in class, and basically it's called transfer learning, right? Sometimes we will find our data as we show you in class. You can download datasets, you can download pre-trained networks, and in this case we're going to use like Mobilenet and others that, for example, if we go again to here, these are efficient convolutional neural networks that we're going to see in the next class, right? And Mobilenet, for example, as also like Inception, for example, Inception V3 are very efficient, like pre-trained neural networks with like 1,000 of parameters. So this is actually very, very, very important. So let me just show you. Since the creation of convolutional neural networks that we're going to check next week, and we're going to understand like deeply how they work and why they are so important, there are like many networks that basically they were created to test, for example, the performance of artificial neural networks. You can find like AlexNet, ImageNet, Inception V3, for example, or ResNet. In this case, we're going to use one specific neural network that is called Mobilenet B2. Actually, this is a small neural network, a small like quotes, because actually it's an architecture, it's a model that is already trained. We have the weights and the architecture already trained in like millions of parameters. And this is actually pretty good because let me see if I can find, for example, we have the reference here. Of course, like each of these things come with a paper. And basically what Mobilenet is doing, basically it creates this network as maintained by Google, for example, and it trains and detects 1,001 categories, right? The why not 1,000 is because the 1,001 category is the background, so it can detect if something basically has no detections. So this is very important because if we see basically here, you see if we see the Mobilenet architecture, we see that these are all the layers, decision, convolutional neural networks, and some activations, and so pooling. We're going to see what pooling is, and it has a fully connected layer almost at the end, and then it classifies at the last layer, right? With using softmax. And in this case, you can see here that it has like 1,000. Basically, it returns like one of the 1,000 categories. So this is very important because now we can use this architecture that we have here and we can take and we can chop it, right? And we can delete the last layer, right? So we can basically say like, okay, give me everything except the last layer that is the output layer, and we can create a new layer that only will output our three categories. In this case, knives, forks, and spoons. And this is really nice because we don't need to train it for like a week now, because we're using an architecture that is like, it's pretty good at detecting things. We can only train it for a few epochs. So we're going to see how that works now. So in this case, we're going to download Mobilenet version 2. To do that, basically we import TensorFlow SDF. And in this case, we're going to import from TensorFlow Hub, we're going to import Hub. And in this case, we're going to feed the Mobilenet URL from the website of TensorFlow Hub and create the object or the Mobilenet based on that. And this is very important. The input shape for our network is 224 and 224 because that's what Mobilenet asks by 3. So basically it's like width and height, and also the 3 channels for color. So if we execute this, it will download Mobilenet, and we are ready to go. In this case, what we need to do, right? We need to freeze our model, right? Our Mobilenet. So basically, we said like Mobilenet trainable false, because we only want to use everything except, again, like the last layer. So for more information about what freezing means, we can check this. Just let me copy this and paste it here. So what does freezing a layer mean? So basically we are freezing a layer in the context of neural networks about controlling the way the weights are updated. When a layer is frozen, it means that the weights cannot be modified further. So basically this technique, we don't want to, again, modify the weights because they are already like fine-tuned, they are pre-trained. So we're going to use that. In this case, right, we are creating a new model, and this is the way we do it. We create a new model using the frozen Mobilenet and adding a output layer that will output basically based on the 3 categories that we have, using the activation that softmax with 3 possible outputs, basically 3 outputs, right? We will get always the one with the highest like probability using softmax. You can always look what softmax is as activation. Of course, we're gonna do it right now, so you are not like here softmax activation. Again, if you saw the Siraj Robal video that is in one of the decks, you can find like why we're using this, right? So basically, it's the one that converts like again like a vector of numbers into a vector of probabilities, and in that way we can basically like then select which one has the highest probability. So we do that, and then this is pretty nice because if we print our model summary, it's basically like all the Keras layers and then our like dense layer with only like 3 outputs, but we can see that we're training a network with more than 2 million parameters, and that is like actually pretty good because we're only training now. You see, because it's a frozen basically it's like a frozen model, and all the Mobilenet part. We have more than 2 millions, but we are only going to train almost 4,000. That is really cool. We need to compile the model, specifying the optimizer. This is Adam. Also, like there are a lot of like optimizers and laws and things like that. We're going to talk about them in more detail in the next classes. Not going like very hardcore in like the theory, but basically have, of course, like gradient descent, stochastic gradient descent, and also you need like you have different algorithms and basically like functions to measure the loss of your data, and we saw that today, right? We used the test data set to measure against the training data that we're getting. So basically, like, how you compare the unseen data versus the data that you are creating to basically have a measure, and that parameter will allow you to basically optimize, right? We want to minimize that. And we want to, basically the metrics that we're going to evaluate are the accuracy of the model. So this is why we're doing this. The categorical cross entropy is very good for classification purposes. So basically we're like calculating the according to categories that we have, right? So in this case, if we compile the model, and then we can train it for a few epochs. So in this case, for example, like 50 epochs is okay. You can train for more. And the way that you do it, you specify the epochs. So basically the epochs have like a lot of steps. So basically one epoch is how many times the model goes over your data. And then using this function here that is fit. So basically you need to fit the model. You're using the training data, the amount of epochs, the batch size. If you have a beefy GPU, you might want to increase the batch size, but with 32, because that's what we specify in our data set creation, it's okay. And we need to specify also what is the validation data, the unseen data, that is the test data set that we have here. So we're going to execute this, and I will pause the video so you can see how it goes. So what we see here, it has been like probably like, you see that it takes like per epoch around like, per step of the epoch, like each epoch. So basically is 11 seconds. So 11 times 14, that is the time. Why 14? Because that's the time that, based on the batch size, it takes for the model to go over all of your data. So imagine that if we are training through all the layers and basically updating the weights or whatever, we will get like not very good results. So I'm showing you this for one specific reason. You see that our loss, basically what we want to do when we're training a model, and this is something also that we saw in the end of 5 examples, our loss is pretty low, right? And it's going, sometimes it goes like, you see here, it's like close to 0.2, then it goes like up to 0.4, then it goes down again. And basically the model, you can see that it's improving, especially the accuracy of the model. It starts with an accuracy of like 50%, and then it goes like really quick to 70, 83, 87, then drops to 84 again, but then it just go up again because it's already like really well like fine-tuned. So basically this is the validation accuracy against like the data that we have. We're still getting like okay results, again, because we don't have a lot of data, right? If we have more data, probably it will take, of course, more time. But I think this is okay to prove, basically to show you the pipeline that we want. If you want to train this with your own images, you can go in the street and take pictures of whatever you like, right? To train, I don't know, pretty much whatever you want. So I will continue this as we finish. We're halfway. The training process has been like 5 minutes or so. So it's going like pretty fast. So let's wait for it to finish. All right, so it finished. It took like less than 10 minutes. The loss is pretty low. So you see it's like 1.7 and the accuracy is 92%. so actually that is pretty good. So now, for example, let's see how the training go. How did the training go? We're here just plotting like the accuracy, the validation accuracy, and the loss. So you can see that it went like very very high, really really fast, right? So that is good because it was already trained. And also the loss. You see, it went like very fast immediately, and it goes up and it goes down. Usually when it comes to images and working with like a little bit of not many data, not much data, it behaves like this. So that is good. So now, for example, we can see if the model is actually doing a good job. So for that, we're just importing some functionality. So like PIL to work with images. We are importing requests to get, for example, like images from the internet, and some imports like CV2 and so on and so forth. So in this case, we have a definition that basically takes an image from the internet. We transform this image into a NumPy array. We talk about that in class as well. So basically, we need to make the machine understand that this is an array. This is a structure of data based on numbers. We resize this to the correct size that we want it for the prediction. So in this case, like 224 by 224. For that, we're using OpenCV, the computer vision library. And here, this is a very important line because here we make the prediction. So remember that in order to train, we use model.fit. Here we just use model.predict, and we reshape our images, our NumPy array, in this way. So basically it's like a 224 by 224 and 3 channels. And what we want to return here is the argmax. Remember, it's the one that using NumPy argmax because it's the probability, the biggest probability, and basically this is just the axis -1, so it will get the right information. So we execute this. Of course, nothing happens because we're not calling here the actual function. We're calling it here. So we have a URL, right? In this case, must be 2 because we are inputting. So if I parts of a knife. So this is an image of a knife. This is an image that just found on the internet of a knife. Sorry, it must be 1 actually. So let's see. Probably it doesn't do anything and needs more training. But if we did this, if we execute this, it's getting the image and it's doing the prediction. And actually, it is it's predicting that it is a knife. So what else we can do? For example, we can just go and say like fork images, and let's say we want to get probably this will be a tricky one. So let's see if we can. This is a fancy fork, by the way. So image address. Let's see if we can. Yeah, you're okay if the address, like basically it finishes with a JPEG extension or whatever. So now we're using this, and now in this case, if it does the right prediction, it must output a 2. Probably it can be confused with a 0. Let's see. Yeah, you see, it's basically because the data is, we don't have a lot of data. It's predicting that this is a spoon, probably because of this shape. Let's try with another one actually. Something that looks less like probably this guy. Copy image address. Let's just verify that this is actually a valid address. Yes. So if I replace this, then I can actually just delete this part. We don't need that. Yeah, it's still 0. So we see that it probably is like it needs more epochs, for example. But the knives, for example, it just predicts like very well. So that is fine. I mean, this proves our concept And one thing, so we don't lose what we have, we can always like create a folder to export the TensorFlow model to serve it. So basically now we have a classifier of kitchen items. We can save the model with model.save and specifying a output folder. And finally, we can zip this to download it. So if we do this, for example, we see that the output folder has the kitchen model, and the kitchen model, oh, actually, I just erased everything, but we can download now this and we can serve it in a server and so on and so forth. So with this pipeline, basically you're going through basically like a very quick, kind of simple full pipeline of or methodology on how to work with data and train it. And this is very important because we will do this in the semester. So I hope you like this video, right? I will be posting all the videos that I make for the class also on my YouTube channel. So thank you very much.